Okay, so as you know, if you've been to classes before, Hoosier always wants a safety topic at the end. Part of the culture. Electricity, when used incorrectly, can be hazardous. We want to make sure we're talking about some safety things. So in the past, I've talked about grounding and I've talked about arc flash. And so the Hoosier folks said, well, tell us some things in your consulting practice. Particularly, you mentioned to us at, dinners and lunches sometimes about some of the expert witness stuff you're doing where somebody got hurt. And when you get called in to testify at these things, what was an issue? What are the safety things where something fell through the crack and somebody in a plant got hurt with electricity? So I kind of racked my brain and said, what are my typical attorney calls that are looking for an expert witness to testify, either in defense of the company or in support of the plaintiff type thing that got hurt? And I said, okay, if I really start looking at what I get involved in, I surmise right now that many of the really young folks coming into your facilities that may have some experience with equipment and maintenance practices don't understand as well as maybe they should the difference between 2- and 3-wire control of motor starters and motors, and the differences in safety and automatic starting capability that 2- and 3-wire control considerations and manual and automatic overload reset imply. And the reason I say that is because I do a number of these different things where somebody gets hurt when they didn't realize there were automatic overload resets. They assumed because the equipment was not running that the power had been locked out and tagged out. They were messing around with shafts or gear or trains or something when that automatic overload reset, turned the system back on, lost fingers, hands, arms, etc. So I don't know for sure. I'm not at every accident. But when I look at these accidents, they're all younger than 25 years old. They don't have much experience out in the facility. They were all trained in lockout tagout procedures by their company. But somewhere that lockout tagout training and that idea of ensuring the energy was removed before I put my hands in there didn't make it into that person's practice. Okay? And if I talk to other people, we see the accident numbers rising in that same scenario out there. And they're all younger than 25 years old, which tells me, at least without doing much, youth and inexperience. We didn't take lockout tagout as seriously as we should have, that type of thing. Capacitor banks. We talked about power factor correction. Now I put a device into your facility that might be in your circuit or your main service that stores energy even after you flip the main disconnect before it. So now I have to make sure under my lockout tagout procedures that I remove stored energy from devices, which a capacitor will do. It will store energy. So now before I can work on equipment safely with lockout and tagout, what are the things I see that people sometimes forget about in removing that stored energy from the capacitor bank before they work on a system? And then VFDs, kind of a strange one, and I thought when people started asking me, why in the world do you want to do that? And then they gave me some reasons that made sense. What is my concern and why have some people been hurt when people put a load side disconnect between the VFD and the motor? What do I have to think about now in terms of safety procedures, special training, by having a disconnect between the VFD and the motor, and somebody walking up, instead of turning the VFD off, opening that disconnect to disconnect the motor while the VFD is still running? And if you've ever seen any videos on YouTube or anything else, bad things happen when I do that. Number of things the drive can do. So I said those are the three things that I would essentially say that I see that are in the back of my mind where I say okay, good companies like most of you that come from today, that come to classes, have a lockout tagout procedure. You use it, you train people. You're pretty cognizant of people that come into your plant, making sure they understand what your procedures are. But somehow something slipped through the crack and now somebody got hurt significantly. So what do we need to think about? Maybe doing a better job of relaying to some of those younger folks why we care about these rules and what can happen. So typically a standard magnetic motor starter is going to have a starter, going to have some overload relays then, and if we use a start-stop station, push buttons, we understand how we wired it up, how that system works. We've done that forever. Okay, so that allows automatic and remote control, which we like. Higher cost but greater flexibility than a manual motor starter that the code lets us use on a small motor. Okay? So we've got those types of things. Now, one of the questions I get a lot is, why does the National Electric Code make me have overload protection at the starter if I have a motor that has overload protection at the motor? So I can buy motors that have an internal overload device. And motors that have an internal overload device can have a manual reset overload or an automatic reset overload. And the idea in the National Electric Code, which is safety, is we don't care about that device. It's optional or supplemental. We care about the one in the starter panel that we're going to use in terms of all of our safety things as the primary. Fine, you want to do that, you can put that in there. But the ones in my starter panel, okay, those are not going to be automatic reset. So now, what's an implication in using a motor with an automatic reset in the motor for overload? What if I'm using two-wire control? I have a float switch or a thermostat, turning that motor starter on and off. And the overloads in the starter panel don't trip out, but this overload trips out. At what point does a person, subcontractor, or young person in your plant, because they see the contacts in that float switch or that thermostat or should be closed and the motor's not operating, assume the power's off and violate lockout tagout procedures and now start messing around with the system without ensuring the power is off? That's essentially, and I start asking these questions from people that get hurt or having other people ask them. It's like, well, nobody told me. Well, you went through lockout tagout training, yeah. But I just assumed if that motor wasn't running and the contacts were closed up in front of it, somebody must have turned it off somewhere else. Okay? Bad assumption. So that's the type of thing that I see and get involved in terms of, okay, what fell through the cracks? It wasn't the training, it wasn't the lockout tagout procedures, because the company did good training and they provided equipment, they provided PPE, all the other stuff you're supposed to be doing. Somebody still got hurt. Okay? I always tell people, depends on who's asking the question, okay, Mr. Stark, what would you have done differently in terms of the company protecting its workers if you knew that motor could come on automatically? Well, one option is to make sure only qualified employees can get near that motor by barricading it behind a fence or in a room where the access is controlled, like NFPA 70E says you can do. The other part of the question that I just mentioned, about half of those people getting hurt are unqualified employees. How did an unqualified employee get so close to that piece of equipment? In one recent situation, the plant was doing an overhaul and it was everybody on deck. And so we had office people out there assisting maintenance people, handing them tools, taking the tools, cleaning them up and putting them back, and things like that. That probably, if you look at the letter of the rules of the OSHA law, were in violation of being too close to that equipment without being trained to understand the real true hazards of that automatic reset and that piece of equipment. Okay? So that's what I see in terms of this issue out there. 2-wire and 3-wire control, just to think about that. 2-wire control allows use of automatic control devices. 3-wire control, I'm going to use a start-stop station with push buttons. If the stop is pushed, the system will not automatically restart. So that start-stop station, if my magnetic starter trips out because an overload tripped out, it doesn't matter. It's got to be the start button pushed again. But in that 2-wire control with the thermostat, a float switch, a pressure switch, if that overload trips out and the contacts there are still closed and it's an automatic reset, it's coming right back on. It might overload again in 10 minutes, trip off again, but we've got that issue. So I've seen places where things broke down and people weren't trained to understand that it could come back automatically. There was no signing to say this machine could start automatically, etc., etc. Those are all conditions you see out there where somebody screwed up. If you look at a ladder diagram or a wiring diagram of what's going on with 3-wire control, it makes perfect sense, because if that starter is de-energized because the overload tripped out, then to get that starter and that motor down here back on, I have to push the stop button or start button to get it back on. Okay? Why don't people like that? What if the power went off? So the power had a little blink. And now what do I have to do to go turn that pump back on? I have to walk out there and go to the button after the outage. And if I have 50 pumps I have to turn back on, pretty soon I'm saying, this is a load. I don't like this. We got to fix this. Okay? Well, there are ways to do that. I've seen one where people essentially pulled that out and they essentially just put a timer in there. And they used a disconnect in front of it. If the disconnect was closed, the power went off. A minute after the power came back on, the timer closed the contacts and the motor came back on. And somebody got hurt. So, less safety concern for unqualified employees. Troubleshooting. If the motor won't start, the first thought is power, and then check the overloads. But if I go to 2-wire control with that float switch, now if that float switch is closed, the overloads kick out, and then they come back on automatically, that thing can still start up and run with no warning. Okay? So that becomes the issue. I just have a feeling that maybe we are assuming the young folks coming in understand this, and nobody's ever really sat down and explained, well, this is how the system really works, and this is why we trained you on lockout and tagout. Can you put those two things together now? Because somehow, at least some people aren't putting that together based on the number of these that I end up with. So, I can start automatically. Possibility for unqualified employees to assume the system's shut off even though no lockout tagout's been completed. Warning labels on equipment that might start automatically. Use lockout tagout before service and maintenance of any type. Something like that. Train unqualified employees on the danger to make them qualified to understand the hazard and guard the equipment by location or access so those unqualified folks can't get to it to screw up. Those are some options then typically that can be used to, okay, if we've got a concern for this, what can we do? Now, power factor correction, maintenance and safety. Under normal conditions, capacitors should operate trouble-free for many years. Things like harmonic currents, high ambient temperatures, and poor ventilation can cause premature failures in power factor correction capacitors and circuitry. That can lead to substantial increases in energy expense and create the potential for fires or explosions and other unsafe conditions. It's important to inspect power quality or power factor correction on a regular basis to ensure they're working properly. If I look at most manufacturers' literature, it recommends preventative maintenance on power factor correction capacitors twice a year. So every 6 months, you could assume. So large capacitor hazards, storing energy, large amounts of energy, even after the equipment's been de-energized upstream, it can build up a dangerous residual charge without an external source. Okay? So with capacitors, as part of my lockout tagout, I want to make sure after I disconnect, I discharge the capacitance that stored energy into the ground, into the air, both, whatever means we're using. Another hazard exists when a capacitor is subjected to high currents that cause heating and explosion. Grounding capacitors in series, for example, can transfer rather than discharge the stored energy from one into the other that already is full, and then bad things happen. An internal failure of one cap in a bank frequently results in an explosion when all the other capacitors in the bank discharge into the fault. The liquid dielectric in many capacitors or its combustion products can be toxic. So even if the shrapnel didn't get me when I was in the room, the fumes could still cause some damage to me in terms of now I was in the wrong place at the wrong time. Safety concerns. Most PFC capacitors are equipped with discharge circuits. When that circuit fails, a shock hazard exists for an extended period of time. So when I get involved in power factor safety issues where somebody got hurt, typically 8 out of 10 times the discharge circuit has failed and it was never maintained. So people just assumed there was a discharge circuit and it would work. But it had not been maintained, it had failed, and so when they made a faulty assumption like that, bad things happened. And typically we get that capacitor then feeding into the others or something that wasn't expected, feeding to the wrong place, and somebody gets hurt. So capacitor bank maintenance requires training specific to the equipment, its application, and task you're expected to perform, as well as understanding proper PPE. Additional hazards are involved in working with current transformer circuits, including the wiring and shorting block for the cap bank. The CT itself is normally located in the switchboard, not in the cap bank enclosure. Even after the capacitor bank has been de-energized, there's a danger of electrical shock from the CT wiring in the other location. So if the CT circuit is open when there's a load on the switchboard, the CT can develop a lethal voltage across its terminals. Okay. So I said the discharge circuit, 8 out of 10, there's your other 2 out of the 10. So general procedure, often overlooked as a source of voltage when checking de-energized circuits. Okay? Most of you have probably had it drilled in your head. Not only do you essentially disconnect the circuit, but then you have to release stored energy in that equipment, wherever it is. Capacitors, no different. So, how do I know where all the capacitors are? You have to take me around to show me, or give me your schematics and diagrams. What if those aren't up to date? Okay. Potential issue. Isolate the capacitors. If the caps have internal drains, give them enough time to drain. Most folks will say at least 5, if not 10 minutes, just to be sure. I've seen some where the people were in a hurry, they only gave it a minute and a half, it wasn't fully discharged, problem.
Short circuit and ground the capacitor by first connecting a conductor to ground and then to the capacitor. These are all things from capacitor, power factor correction capacitor manuals from the manufacturers. Okay? Visual inspection. Look for bad equipment. If you open the door and the caps are laying down at the bottom of the panel, you probably know you've had some vibration and a mounting issue. Something like that. Look for those signs. Infrared inspection is starting to catch on for cap banks as well. Not so much necessarily to see bad connections, although it helps with the shorting circuit, but to now see which caps might be charged and which ones aren't. Because those charge caps will be higher or hotter than a discharge cap. So we went through the procedures. Did we really discharge all the caps? Or was there something we forgot and we got one or two sitting there that's not discharged? We can see that on an infrared heat gun. Okay? So some of those types of issues become important. Is automatic discharge grounding required? Okay? Well, maybe. Depends on the class of the capacitors and the joule size of energy that they store. Capacitor fusing. Okay, that becomes important. How you fuse those capacitors. Because if they're in parallel, okay, individually fused to prevent the stored energy from dumping into a faulted capacitor. So there are things like that you take into account when you install them. Care must be taken in placement of automatic discharge safety devices with respect to fuses. If the discharge will flow through the fuses, a prominent warning sign has to be placed at each entry indicating each capacitor must be manually grounded before work can begin. Some of the grounding issues, if you look at what the manufacturer suggests in terms of fully visible manual grounding devices to render the cap safe while they're being worked on, clearly mark the grounding points and use caution to prevent transferring charges, as we said. All grounding hooks must have crimped and soldered conductors, be connected such the impedance is less than 0.1 ohm to ground, have a cable conductor size capable of carrying any potential current, be in sufficient numbers to conveniently and adequately ground all designated points, and be stored in the immediate area of the equipment in a manner ensures they are used. This is what the OSHA inspector's checklist looks like. OSHA inspectors have checklists. If you get a surprise inspection, okay, in terms of your capacitor room or place where that cap bank is, these are the things they're going to look for and check. And if they get all the checks, you've done that, okay, fine. It doesn't matter if there's bad connections or other types of things. This is what they're looking for. That will get you a fine. Okay? Voltage indicators that are visible from all normal entry points can also be provided. Don't have to. Now, the final safety thing for the day, just an FYI, is it okay to use a disconnect here between the VFD and the motor? So, most VFD manufacturers say yes, provided you use an auxiliary contact to ensure that if this device is open to disconnect the motor, the drive is simultaneously shut off. I can't just have a disconnect here that opens the motor and leaves the drive running. Okay? And that's relatively new from most of these manufacturers. Many of them have said in the past, no, you can't do that. Or doing that voids the warranty if it's just a disconnect for your drive. I know, by the way, not only it will void the warranty, but your drive might blow up. And we're not responsible for that. Okay? And so there are various reasons. Anybody think of reasons people put that disconnect in there? Well, the common ones I hear is the drive and the motor are farther than 50 feet. And what does the code say about a disconnect for a motor? Within sight of and within 50 feet. Okay. So now, if that's farther than 50 feet, I need a disconnect device to meet the code requirements there. Inspector said so.
So why would I want an add? There's your slide. Some VFDs are rated as motor disconnecting means. Some technically are not. So if my VFD is not rated as a motor disconnecting means, the inspector says, I don't see any rating as a motor disconnecting means on that brand of VFD, you need a disconnect. Okay, now I need one. Okay. What if the VFD can't be located within 50 feet or sight? Now I need one. Okay. So those are reasons. So why the concern? If that disconnect is closed, then the VFD will operate normally as if the disconnect were never even there. The potential problem arises when the disconnect is opened or closed while the VFD is running. That's commonly referred to from the manufacturers as slamming the motor. Opening that disconnect to shut the motor off with the VFD operating and not shutting it off simultaneously. This typically produces a voltage spike or transient that can cause fault alarms in the VFD, and many drives will interpret the situation as a speed up condition and start raising the frequency in the voltage that it's sending out from the drive. If the disconnect is then closed and the drive is outputting 60 hertz from its speed up to full speed condition, it will trip the VFD with a high potential for damage to the VFD, as in it might blow off the wall. That type of high potential damage. And if you're standing near there, the shrapnel and those things, the concussive blow can be pretty bad. Oh, and by the way, the manufacturers say that's not covered under general warranty. That's on you. Another thing to consider is that many disconnect switches were not designed to make or break under load unless they have a horsepower rating. So I see people that put that disconnect in there and it's not a horsepower rated disconnect for a motor. It's an amp rated disconnect only. And so depending on what that motor's driving and the inertia, you open up the contacts and the electricity, because of that inertia in the motor, is still arcing across those contacts. And that becomes a problematic situation. That's a safety issue for a technician with his hand on a switch that's not rated to handle what is being done to it. The switch could fail if operated under load. So the common solution is to add fast-acting auxiliary contact on the disconnect that triggers a freewheel stop on the drive before the main three-phase contacts open. So this allows the VFD to shut down when the disconnect is open and then re-engage when the disconnect is closed again. And I avoid that slamming of the motor and the drive seeing a speed up condition and potentially getting to the point I've got a problem. Refer to your drive's programming manual for instructions on programming that input as a freewheel stop when I do that.